All right, welcome back, folks. Today we'll be talking about sedimentary rocks and how we classify them, okay? But just as always, do a little logistics, right? So this week, it's all about sediments and sedimentary rocks, and you have several things due this Sunday, right? The lecture quizzes from each day, right? So Monday, Wednesday, and Friday. It's really short, it's on Blackboard, as well as reading quizzes for Interlude B in Chapter 6. And then lab this week is about sand. You'll read an article from the New Yorker and you'll answer questions and look at some satellite image time lapses of some of the places that are mentioned in the text and processes that are relevant for how sand is made and exploited as a natural resource. And you'll also answer questions for those. And then just a final word about that is that it is okay to work together on things, but you should be submitting your own work. So do not copy word for word other people's work. It's pretty obvious to us when you guys are copying each other's work. So please submit your own answers to these questions, okay? All right, and then again, there will be an exam next week. And I will post the exam on Blackboard, and you will be able to take it at any time from Wednesday morning, April 8th through Friday, April 10th. It is open note, open book, and you will testify that you are respecting and adhering to the honor code, that you did not cheat or cooperate with others while taking this exam. You will have 1 hour to complete it. And if you have special accommodations through EVM, I will respect those. And it is going to be similar type of format to the last exam, multiple choice, fill in the blank, the diagram, matching, that sort of thing. And again, the material that we'll cover goes from geologic time, plate tectonics, the rock cycle, magma and igneous rocks, volcanoes, and weathering. Okay, the sedimentary rocks, what we start talking about today, will not be on the exam, okay? It'll be on the final. All right. And I will work on a study guide for this that I will try to post by the end of today, okay? All right, so let's go to sedimentary rocks. So, all right. An important thing that we need to keep in mind is why do we even want to care about sedimentary rocks? Well, if it were not for sedimentary rocks, we would not know anything about the history of the climate or life on this planet, right? So in all of what we learned about geologic time, right, which was initially based off of the fossil life that we found in different rocks around the globe, that was really the basis for a lot of our understanding of geology. And fossils are only found in sedimentary rocks, okay? So they give us a history of life. And then we also learned from our way back at the beginning of the class about climate that these types of rocks, sediments, record changes in Earth's climate and environmental conditions. So what goes hand in hand with the evolution of life is also how Earth's climate has changed through time, right? And how life has adapted and evolved through those changes in climate. So that's more the scientific reason that that's important for us. But at a more real world level is that sedimentary rocks are often what we use for building materials, right? It can be sand that is going to be used in roads to make concrete, limestone that can be used for building actual buildings, sandstone rocks to make cobblestone roads, to build pretty buildings at a university, right? So it's important as a building material. And then finally, and probably the most important thing about sedimentary rocks, at least in my opinion, is that they are where all of our, or a majority of our energy resources come from. And this includes coal, oil and gas, and as well as uranium. Uranium is actually found in sandstone rocks commonly. And another type of sedimentary rock, which is an evaporite, a salt, right? So lithium, which is really important for making renewable or reusable batteries, even for green technology, right? For hybrid cars or electric vehicles, require the use of raw materials. So sedimentary rocks are important because they host all of these resources that humans for the last 150 years, and especially today, are completely reliant upon. So what I'm showing in the diagram on the right, I'll turn off my video here for a second, is that this is how we progress from an ancient environment into a fossil fuel. So marine plants and animals, live out in the ocean, and then they die and they sink down to the bottom of the seabed. It gets covered in sediment, and over time, sediment accumulates over the top of it, and it compresses that dead material and breaks down into hydrocarbon molecules, which is oil and gas. And then eventually that oil and gas moves around in porous or rocks that can hold that liquid or gas hydrocarbon compounds. And that's where we get most of our energy from. So this is really important in understanding how sedimentary rocks form and the different environments they reflect. Okay. So we have several different classes of sedimentary rocks, and we will go through each of these in detail. But we will start with clastic rocks, which are fragments of broken down rocks and minerals. So these are things like sandstones and shales, right? Ones that you've heard of. Biochemical sedimentary rocks are those that are made out of shells or microfossils. So, out in the ocean, you have shells that are made out of calcium carbonate, and enough of those, like clams and mussels and whatever else makes its shells out of calcium carbonate dies and then accumulates into layers of shell hash, which can become biochemical sedimentary rocks. Or you can have plankton like diatoms, which are made out of silica, SiO2, and they will turn into diatomite. Then there are organic sedimentary rocks. And so the word organic in terms of chemistry means the presence of hydrocarbon molecules. So coal is the most important organic type of rock, right? Because coal is just basically a swamp or a marsh which has a ton of input of trees and lots of carbon-rich material that gets preserved in a low oxygen environment and then turns into a coal bed with a little bit of heat and pressure over time. And then we also have chemical rocks that are precipitated or evaporated in water, and that can be things like limestone or salt. All right, so how do we get clastic sedimentary rocks? These are probably, the most important in terms for you to understand how we end up with sedimentary rocks. So the first thing we need is we go through the weathering process, right? We have to break down solid bedrock somewhere else through physical or chemical weathering, like this granite boulder that is weathering out in the desert of Antarctica. And that makes tinier little fragments that can be eroded from the landscape. Then we need to erode fragments, right? You have to tear them off from somewhere in the environment. So like a cliff, right? Erosion in action. There's a bunch of rock fragments forming, okay? And then you need to move or transport those fragments of rock, right? And so rivers are one way that we can move around sediments, right? So here is a meandering river in the Bolivian Amazon, and you are seeing in the brown tan sediment moving through that river, and the change in the course of the river reflects the erosion and deposition of that sediment across this river landscape. When you reach a point where there's not enough energy for those fragments to be transported, they are deposited. They settle out of solution and lay down onto the bottom of a basin. So out in the ocean, once you get away from the rivers and away from the waves at the beach, currents are pretty calm along the bottom of the ocean and sediment will fall out. Okay, so we still are not at the rock phase. So in order to make it a rock, we have to have lithification. And that is the process by which these clastic sediments or fragments are compacted by sediments that lay down on top of them and then cemented together between grains. And that's how you end up with a clastic sedimentary rock. So how do we classify clastic rocks? Right, so just like how we classify sediments, the most important aspect is the size of the grains or the fragments or clasts that are in your sedimentary rock. And I'll describe these in terms of increasing grain size from fine to coarse. So if you have a clastic rock that is mostly composed of clay, that is a shale, right? So if you're from upstate New York and you've been driving along the New York Thruway, you've seen a lot of black shale through road cuts along the road, right? So that's clay-sized sedimentary rock. Silt, so slightly more coarse, is a siltstone. And then sand turns into a sandstone, okay? And if you start getting bigger and bigger, pebbles, cobbles, boulders, you end up with what we call a conglomerate or a breccia or a diamictite. And each of those three have different meanings based on the texture of the rock, but the grain size is large. So the size of the clasts in your clastic sedimentary rock is really a reflection of the transport energy in the depositional setting. So you can think of, if you go out in the summer when it's not freaking cold outside and you go to a little pond in New England and you walk around in the shallow part of the pond and you feel all that muck, right? You're feeling fine-grained sediment that oozes in between your toes. There's not a lot of transport energy, right? So you're not going to have big sands in there because the water's not strong enough to move larger grains. It can only move and deposit out the fine-grained sediment that turns into mud. Then think about going on a hike here in Vermont, right? You go to the potholes at Bolton, right? And those are raging rapids. And if you look at the size of the sediment in that river, it's much larger, right? There's boulders and cobbles. When that stream floods and you have a lot of energy moving through that stream, it can transport clasts that are the size of cobbles and even boulders. The next way that we classify clastic rocks is based on their composition. So the composition is really a reflection of the different mixture and proportion of minerals or other rock fragments that you find in it. So there are really three main classes of sandstone that we can classify based on their mineralogy. So if we have a sandstone that is completely made out of quartz, right? If you took a hand lens or a microscope and looked closely at that bright white rock, you would see just things that look like this, right? You would just see little individual quartz grains. If you have a sandstone that has a mixture of feldspar minerals, mica, and quartz, the overall color of that rock is going to be more of an orange color, and we call these arcosic sandstones. If you have sandstones that are made out of mafic minerals, right, things that are like olivine or pyroxene, the darker colored minerals, we call it a greywacke. Okay. The next way that we classify clastic rocks is based on the shape of the grains. We call this the angularity or the sphericity, right? And really all this means is how sharp or how round are the edges of individual grains, right? So we can go from a really angular sculpted grain, an angular, up to something that's totally rounded, right? And the rounding of those rocks, or those grains rather, is really due to collisions with other clasts, right? So it's not really so think of like going up to a stream up in the Green Mountains, right? And you come across some stream bed where all of the rocks in the stream are kind of rounded. They are round not because of the water that is flowing over them. They are round because those individual cobbles are banging against each other, right? They are sculpting each other into a more rounded shape. The next way that we classify clastic rocks is based on how on their sorting. And the sorting is the proportion of clasts in the rock of similar size, right? So we've talked about this when we talked about glacial sediments, specifically diamix or till, because they are poorly sorted, meaning that there are many different grain sizes present in your clastic rock, right? You have cobbles all the way down to clay and everything in between. A rock that is well sorted is one where you only have really one grain size. So in this picture, right, everything looks kind of the same size, and that means it's well sorted. So I'll use a food analogy here, right, is if you think of trail mix, right, it's very poorly sorted. There's a complete mixture of different things of different sizes, right, like M&Ms, almonds, sunflower seeds, Brazil nuts, right, like all these different sizes, versus if you pour out a bag of M&Ms, right, everything is the exact same size. That's very well sorted. And then finally, we classify clastic rocks based on how they are held together, their cement. Is it held together by quartz grains? Is it held together by calcite? Or is it held together by iron? So if it's held together by a silica cement, which is quartz, we call it siliceous. If it's held together by calcite, it's a calcareous rock. And if it's held together by iron, it's called ferriferous. So this is actually an iron ore, but it's a sandstone that has been cemented with iron oxide. When we put all of these classification schema together, we have a way to categorize any clastic sedimentary rock that you pick up, right? So the way that you go through this is by first describing the size of the rock that you see, right? Or the size of the grains in the rock. If they're coarse, if they're medium to coarse, fine, and very fine. And that tells you if it's a sandstone, a siltstone, a shale, or a conglomerate, breccia, or diamictite, okay? And then you want to look at the individual grains in your rock, right? So if they're, really well rounded, right? That tells you that, and it's all pebbles, then it's a conglomerate. If things are angular, it's a breccia. If they are giant clasts in a muddy matrix like glacial till, it's a diamictite. And then if you have a sandstone, you could look at, what is the composition of the grains? Is it all quartz? If it's all quartz, it's a quartz sandstone. If it's quartz and feldspar, it's an arcosic sandstone. If it's made out of other rock fragments that are sand-sized, it's lithic. And if it's made out of greywacke, which has like mafic minerals and other rock fragments, and they're all sand-sized greywacke. Okay, so we can use this systematically to go out anywhere and describe the type of sedimentary rocks we have. Okay, but the next important thing that we have to remember here is that the transport medium, right, how the sediments are being moved across the landscape and how quickly those sediments are being moved helps determine what type of sedimentary rock you end up with, right? So if we think of sand dunes, right? Sand dunes are made through sediment that are being blown around in the wind and piling up. You're going to end up with basically one grain size, right? So very well sorted, because wind is only capable of transporting just a very narrow range of sediments, right? Dust, fine-grained stuff, is going to go far and circulate in the atmosphere, but sand takes quite a bit of wind and energy to move across the landscape. Those little sand grains are going to be bouncing around and running into each other and abrading each other, and they become more well-rounded, right? Then we could think of another way that you could move sediment around, right? Which is through glaciation, right? And we know from what we learned about in glacial sediments that you end up with things that are very poorly sorted, right? You can have things that are boulders all the way down to clays. Things can be angular because they just get dropped off the side of a mountain and moved by the glacier. You could also have grains that get really well rounded by being underneath the glacier and being ground up along the bed, okay? And then we can think about, what about water that is, or what about sediments transported by water? So water is capable of having really different velocities, right? Think of the different, stream flows that are possible, right? You can think of it like you going on a hike, right? Some streams you could easily walk through, right, and not be swept away, okay? Those types of streams are going to be only capable of transporting small grain sizes, like little sand or less. But if you go to a big raging river, one that you cannot stand up in and it's too swift to move you, it's going to be capable of moving cobbles and maybe boulders, okay? And as those rivers transport sediment downstream, individual clasts are banging into each other, and that helps them become rounded, okay? So we can again think about grain size and the water velocity of different depositional environments, okay? So if we have the water velocity of like Lake Champlain, right? You go out towards the middle of the lake, and you're walking around like on the bottom of the lake, there's going to be very little current, right? It's very calm, and so only the finest grain sizes can float. Everything else will fall out of solution. So environments where you have really low amounts of energy, you are going to only find fine grain sizes, clay and silt. Versus if you go to a small little stream, right? Like you've probably seen this like at the beach where there might be like a culvert draining some water out across the sand, right? There's enough water velocity to move that sand and transport it and carve out and erode little river plains, right? Then if you go to an extreme level of this, right? Thinking about like a really high gradient, meaning very steep alpine setting where you have huge boulders in the stream bed. So the only way that you could possibly move boulders of that size is with really high stream energy, high stream velocity. Okay, so I wanted to show this video because there's another way that we can move sediment, right? Water, wind, and ice are probably ones that make more sense to us in our brains, but a really important way that sediments can be moved, especially in areas with a lot of topography, a lot of steep slopes, is through landslides or debris flows. And debris flows are the combination of a lot of water, steep slopes, and a mixture of sediment that is eroding off of the landscape. And if you have all these three things together that are triggered by like a big rainstorm or snowmelt, you can end up with really massive debris flows. So this is a video from Switzerland where engineers have sort of isolated this one channel on the landscape that lets debris flows flow through them without damaging too much infrastructure around it. Okay. So this video is a little bit long, and I'm not going to watch the whole thing, but you can see here, there's a little bit of water in the stream right now, right? And we keep going. Oh, there is more water. Okay, more and more water. So the velocity is increasing and increasing. Okay, still going. Ooh, here we go. All right, here comes the debris flow. And I want you to look specifically at the size of the material that is being moved down the stream. Okay? You are seeing boulders, right? Some the size of a car or like a bus being moved under an immense amount of energy, right? Look at all of this hash of material that's coming down in the main channel of this debris flow. Those things are huge. Okay? So one of the most important things about clastic sedimentary rocks, right, is the energy of the setting that they were transported and deposited in. This is why when you go up to high alpine areas and you look along the slopes of a mountain, right, you'll see like big boulders and stuff on the mountainside. The only way that they can get there is through, steep topography, and if it gets confined into a channel with a lot of rainfall, you can end up with a debris flow. Right? And it's hard to see in here because this just kind of looks like, like a chocolate milkshake, but there are large boulders being destroyed and moved down through this channel. Okay? And it starts to die out. But anyway. So that's clastic sedimentary rocks. So biochemical sedimentary rocks are those that form through the interaction between organisms and geologic processes. Okay? So the easiest way you can think about this is that animals make shells, right? So like clams, right? They make a calcium carbonate shell. And that shell they developed because they are pulling out dissolved ions from seawater and making a shell for them to grow in. You also have organisms like diatoms, which draw on dissolved silica in seawater to make their protective casing for them to live. But then these organisms die, right? And when they die, they float down to the bottom of wherever they were living. And over time, you accumulate more and more shells, or coral, or silica tests, diatom shells, and that eventually will turn into a biochemical rock. So there's two main ones that we need to worry about here. We have carbonates, and the important one we want to know about here is limestone, calcium carbonate. Okay? And then the other type of biochemical sedimentary rock that we are concerned with is chert. And chert is a kind of like a sandstone, that it's made out of quartz, but it's microcrystalline, right? You cannot see individual grains. And chert can form biochemically if you have a lot of opal or siliceous organisms like diatoms. Okay? And we can classify carbonate rocks based on their textures from different formation, right? So fossiliferous limestone are those where we can see the actual shell fragments left over, right? Micrite is a carbonate that's made out of fine-grained carbonate mud, okay? So this would be one where you look at it and you can barely make out individual grains, but you can feel the grit with your finger on them. Right? These are probably like good, like if you're going to go to a mud bath at a salon, they might use something like a micrite. And then there is chalk. And chalk is very fine-grained, calcareous limestone that's made out of dead microfossils like plankton. And one way that you can remember this, right, is that chalk in Greek times was called Crete, okay? And the geologic period Cretaceous, all right, the time of chalk, all right? And where did that idea come from was from the White Cliffs of Dover, which are made out of chalk. Okay? And then how exactly do we know if a rock is a limestone, a carbonate, if it looks exactly like a sandstone? So limestone has the chemical formula calcium carbonate, and the way that we can test this is by dropping a little bit of hydrochloric acid on the limestone to see if there's a reaction. Okay? So this is what happens when you place a small fossiliferous limestone, right? This is not me, so I wouldn't show off the rock that much. Give me the fizz. Let's go. Okay. Puts it in his jar, and now he adds some hydrochloric acid. What you are seeing here is a chemical reaction where you are dissolving the calcium carbonate in acid, and you are producing a solution of calcium chloride, a salt, and then the fizz, the bubbles, is carbon dioxide. And you also have water. Okay? So if you are, out and about looking at sedimentary rocks, and you just happen to have a little bottle of dilute hydrochloric acid, you could do a couple of little drops on it to see if it is in fact a carbonate. Okay? All right, so that is today's lecture, and I will post this now.